In this presentation, we're going to look at artificial light sources compared to natural light. As a point of reference, I have summarized the light saturation and compensation points for cool and warm season turf grasses under natural conditions. To get started, let's look at the most common source of artificial lighting, light bulbs. The light bulb energy is given in wattage, like 40 or 60 or 100 watts. Watts is a measure of power. Wattage or power produces both illumination and heat. Actually, much of the energy generated by a light bulb is lost in the form of heat. Here we have two standard halogen light bulbs, a 60 watt and a 100 watt. I've placed them 5 inches above the laboratory counter and to illuminate onto this white paper surface. We can measure the light intensity on the white surface using a quantum data logger with a light sensor. More precisely, we are measuring the light intensity probably at 4.5 inches below the bulbs, but for this demonstration the exact height is not that important. In this figure we can see the light spectrum of various light sources. Our halogen bulb is not as rich in blue as natural light, but does reflect a similar or at least close to that of the light spectrum. Just for fun, I measured the light intensity of a black light source. Black lights produce ultraviolet light. Black light produces little illumination, and we'll most likely see that in our measurements. In addition to taking light intensity measurements, I recorded the temperature of the white surface in the light bulb with an infrared temperature gun. If we compare the 60 watt to the 100 watt bulb, we see that we generated more illumination or light intensity with the 100 watt bulb compared to the 60 watt bulb. At a cost though. It requires more electrical energy or cost to run the 100 watt bulb. Note the values for both bulbs placed only 5 inches above the surface do not generate the light intensity to saturate cool season turf grasses. Not even close for warm season turf grasses. We have made the compensation point for cool season turf grasses and probably not for warm season turf grasses. Temperatures of the paper have increased 5 to 9 degrees Fahrenheit depending on the light bulb. And the bulb themselves are quite hot. A considerable amount of the energy of the light bulb is lost in the form of heat. With the black light, as expected, has produced little if any visible light illumination. Note the considerable heat generated by the black bulb. Now let's take a big step up. Grow lights, especially in the United Kingdom and Europe, are used on athletic fields where they attempt to enhance the growing conditions of the turf during soccer season. This picture was taken at Emirates Stadium in London, home to the Arsenal Football Club. The lamps are called high-intensity discharge lamps. There are two types of high-intensity discharge lamps, referred to as high-pressure sodium and metal-halide. There is not much difference between the two. The metal-halide may give a better light spectrum, but it may not last as long and is more costly compared to the high-pressure sodium lamps. The high-pressure sodium lamps are popular for stadium grow lights. A sign of high-pressure sodium lamps is the yellowish color produced by these types of lamps. High-pressure sodium lamps produce a rather broad light spectrum. The second type of high-intensity discharge lamp is the metal-halide. Metal-halide lamps produce a broad light spectrum, just a little bit better than the sodium lamps. Similar to the light bulb experiment done previously, I took 400 watt metal halide lamps and placed them in a growth chamber. We made measurements of light intensity and temperature at 5 and 12 inches below the lamps. The light intensity from the lamps is high. Notice the further away the lamp is from the surface that a decrease in light intensity occurs. Actually, the loss in light intensity is not linear. The loss in light intensity graphically looks like a negative exponential curve. In this study, the heat generated is high. From a practical standpoint, when using grow lights in a stadium, the light intensity and heat generated are important considerations or factors in deciding how high to set the lamps from the turf surface. We use 400 watt lamps, and most stadium grow lights use a 400 or similar wattage lamp. However, 600 and 1000 watt lamps can be used, but they are more expensive, and not just from the cost of the lamp, but the electrical costs incurred while running the lights. What about LED lights? LED lights are very efficient light sources with a broad light spectrum. They emit very little heat, especially compared to high-intensity discharge lamps. However, whether in Europe or in the United States, the lamps are used on cool season turf grasses that are growing under low light conditions because of short day length, weather, or shade from the stadium. Commonly, these conditions are the worst during winter. Turfgrass growth is not only dependent on getting enough light, but also the temperatures be warm enough for growth. I think the disadvantage to LED lights is that they do not provide heat or generate heat via the light source to the turf. Let's look at artificial lighting used in a different situation. This photograph is from a golf course in Dubai. In this module, the video Adventures in Golf 24 Hours in Dubai, night golfing is shown. Night golf is common in areas like Southeast Asia and the Middle East due to the oppressive heat that can occur during the day. Night golf is quite popular. This photograph is from TPC Kuala Lumpur in Malaysia, showing the large floodlights stationed through the rough. I thought I would throw this picture in too. I took it in Myrtle Beach, South Carolina. At all these locations, I've been asked, do these lights have a negative effect on turf grass? To gather some data to answer this question, I sent some students out from one of my classes to measure the light intensity of the floodlights mounted across Fred Beekman Park here at The Ohio State University. Using the same light intensity measuring device as previously described, these students measured light intensity of these lights at nighttime. The students measured 0.7 micromoles per meter squared per second. Although the field appeared all lit up and bright, the actual light intensity the turf plants were receiving was basically nothing. Therefore, these lights in this situation have no benefit or detriment to turf grass growth. Just one comment though. The very least, and I mean very least amount of light required by a plant is 20 to 40 micromoles per meter squared per second, which these lights do not provide, at least from this height. Second, to detect any plant response, and in this case would be a slight waving of the leaf, would require 0.18 micromoles per meter squared per second, which again at 0.7 micromoles meter squared per second may induce a little phototrophic response, but nothing that impacts the turfgrass plant either positively or negatively to any great extent. The use of artificial lights in sports fields will continue to grow in the future globally. Increasingly at high-end professional stadiums here in the United States that play football or soccer in the northern regions, we will see their use increased. In golf, there are new units that are just beginning to be tested. We see the potential for these to be used in very specific situations like green that may be shaded.